Hello and welcome to Chapter 7, as this topic is about regression analysis. The learning objectives are to look at how to estimate and interpret a linear regression model, interpret goodness of fit measures, conduct tests of significance, and address common violations of the OLS assumptions. First, what is a linear regression model? Regression analysis is one of the most widely used techniques in predictive analytics. Now remember the difference between descriptive, predictive, and prescriptive analytics. Descriptive analytics, again, are at a point in time based off historical data. Predictive analytics takes it a step further and uses that historical data to provide predictive indicators based off comparing various variables and data values to combine them to see what a predictive outcome may look like based off statistics and significant levels. What a linear regression model does, it captures the relationships between those two or more variables. It predicts an outcome of a target variable based on several input variables. A target variable is what you're looking to find out about. So, for example, let's say you have an hypothesis on a segmentation analysis about customers, and age is your target variable to find out what is the impact to a decision made by someone's age on their income level or academic background or occupation. Right? We're going to try variations of several input variables such as income, occupation, education level to find out if a decision by a customer on age is impacted by those other attributes and characteristics of the customer. A linear regression model also makes assessments and robust predictions by determining which of the relationship matters the most and which ones we can ignore to find out in those correlations of variables which ones truly do matter to a predictive outcome versus those that do not. In a regression model, you formulate a mathematical model that relates the outcome of the target variable, called the response variable, to one or more of those input variables called the predictor variables. So going back to that example, age is the target variable, also the response variable. What is the impact to the response variable of age in my example? The predictor variables of income level, education, background, and also occupation are the various potential predictors. We'll find out which one of those elements or variables are more of a predictability versus the others. We use this information on the predictor variables to describe and or predict changes in the response variable. Further, in a linear regression models are known to perform well for making predictions. Often, they fail to establish a cause and effect relationship between the variables because of the non-experimental nature of most applications. What this means, it does provide a good viewpoint on significance, whether or not an outcome is going to occur, but it doesn't necessarily describe, though, the exact reasons why. So it can provide you an outcome, but then a further analysis on the reasons why from a cause and effect perspective may be needed. A regression model may appear to search for causality when basically detects correlation. Causality, cause and effect, can only be established through randomized experiments and or advanced statistical models. At times, we use a linear regression model as a starting place to find out at least is this target variable impacted by this other variable? Like why does, for example, why is age impacted by education versus occupation or income level? And then you see a correlation. Let's say in this example, age and income level have a direct correlation. That amount of income level for a particular person's age impacts their purchase decisions. Well, the reason of why and how that occurs is an advanced statistical model beyond linear regression. But at least we have a starting place with linear regression to say age and income level do matter. In a linear regression model, no matter the response variable, we cannot expect to predict its exact unique value. So it's not going to be 100% finite. We have to look at other characteristics or statistical models that take it a step further to find a more preciseness on likelihood of something occurring. If the value of the response variable is uniquely determined by the values of the predictor variables, the relationship between the variables is deterministic, meaning that there is a correlation, which means we can at least have some assumption that they do have some relation to each other and impact. However, the relationship between the response variable and the predictive variables is stochastic due to the omission of relevant factors, meaning sometimes not measurable, that influence the response variable. What this means is it may be a correlation, but it may not be as finite as we think. It may be an occurrence or an every now and then type predictor. So that's why we need to understand that it's not 100% exact all the time, that maybe in this example, at times income level and someone's age is a factor to a purchase decision and a linear regression analysis of purchase behavior, but it may also mean that it's not a regular occurrence. In the scheme of linear regression model, you develop a mathematical model that captures the relationship between the response variable, remember, response variable will equal y, and the k predictor variables, which will be your predictor variables. So it would look like this, x1, x2, all the way to xk, right? Now the x is going to be your overall method to say predictor variables. Well, y is the equal to that. The model must also account for the randomness in this part of real life. Remember, in business, things change. Consumer behavior changes, business dynamics, the market. So some of these can be based off predictability, but also has to understand that if something else happens in that predictive model down the road, if you're using your analysis to make decisions, things still can come up and you have to account for that. You start with a deterministic component that approximates the relationships. It gives you a likelihood, a relationship match of some kind of percentile or percent of likelihood. Then add a random error term to it, making the relationship stochastic. Use economic theory, intuition, and statistical measures to determine which predictor variables might best explain to the response variable. It still means that while you have a finite kind of conclusion on some type of correlation or relationship between the target variable and predictive variables, you still need to take into account intuition, experience, knowing your business, knowing theory of the business, and tying that to it for correlations and assumption-based directions. Remember, business analytics provides insights and assumptions at times. It's not always 100% exact, but if we can provide some statistical output of data that provides inference and overall ability to provide directional insight, we're still providing more information than we did before to get closer to a potential decision or outcome that we're looking for in the business. In a regression model treats all predictor variables as numerical. A numerical variable assumes meaningful numeric values. A categorical variable reflects categories. So remember again, predictors must be numeric, has some type of way to transform those data values into numerical values. Where categorical is just that, categories. A dummy variable is used to describe two categories of a categorical variable, denoted as D. Indicator or binary variables, so D equals 1 if for one of the categories, or D equals 0 for the others. So you would actually do 0 or 1 to provide categorical variables. For example, in income level, you may do $10,000 or less would be one category, and then $10,000 to $20,000 as another category. You always have a baseline, which would be 0. The category with D equals 0 is called the reference or benchmark category. So it's at the minimum, at the baseline would be that. All comparisons are made relative to this category. So for example, if we wanted to base something off the $0 to $10,000 baseline, any income level higher than that, what is the significance of that, right? If you're trying to do some type of baseline measurement to say at minimum, this is what the D equals 0 means as a benchmark, a starting place. This is what a sample linear regression model would look like in a calculation or formula. A simple linear regression model uses only one predictor variable. So y equals the b0 plus b1 x1 plus e. So the b0 is the unknown intercept. We don't know what that is yet. b1 is the unknown slope. b0 plus b1 x1 is the deterministic component. And e is the stochastic component or random error term. The expected value of y for a given value of x1 lies on a straight line. So from a slope perspective, we'll find out the predictability based off how we look at that random error term. Remember, a random error term will exist because we're not going to have 100% finite solutions. Let's take a look at this from a graphic perspective. As you can see here, a positive linear relationship is where your E, Y, and the X axis as well has a straight linear correlation that the numbers are going to have a correlation between each category you're comparing it to. In a positive sense, the more we go up from the baseline number, the more that each segment, or let's say increment or intervals of that benchmark goes up, it's a linear regression. It is a positive linear relationship. A negative linear relationship takes a downward slope, where that if you started at a higher baseline of B0 on the y-axis, that each time you incrementally move towards each set of data or interval, it goes down in slope, meaning that it's a negative linear relationship, that it's not significant. There is no linear relationship if everything is 1 for 1, meaning that there's no correlation, there's no exact relationship, and you have a straight line across the y and x axes. So what you're looking for to find significance in the data, if there's a relationship, is that positive linear relationship on the far left. If you get any to the right, you have some type of way to at least tell you that these variables do not have a correlation. So it doesn't mean that you did anything wrong. It just means you have an exact view now to say in a negative or non-linear relationship, there is no correlation or positive kind of impact between each of the variables, the predictor and the target. Now, that was for one type of variable. Now, if we want to take it a step further, a model with more than one predictor is referred to as a multiple linear regression model. Really what you're doing here is you're adding multiple various predictive variables into one set to take a view at relationships between, let's say again, age and income versus age and occupation. Well, if I want to compare the two, age and occupation versus age and income, this type of model is what you may do. You replace x with a d or dummy variable, and then you set a population parameters. B0, B1, B2, all the way to Bk is each set of variables that are there. So you have age and income, age and occupation. You could even add the other age and education. Each one of those is a group or set. A sample data and observations of the overall number of observations. So for this, I have 3 in my example. Age and income is 1, age and occupation is 2, and age and education background is another number observation. Use the sample data to obtain this, which are estimates of the overall values. Okay, so what you're doing is you're doing a linear relationship and comparing and contrasting each of those relationships between the target variable and its predictor variable. This is what a formula would look like to form that sample regression equation. Following this formula, where the y and the y hat above it is the predictive value of the response variable. It gives specified values of the predictor variables. The difference between the observed and predictive value is the residual, so anything left over after that. Ordinary least squares, or OLS, choose the sample regression equation by minimizing the error of some squares. You have a desirable properties if certain assumptions hold, and it gives an equation the closest to the data. So you're going to find a very close variance, plus or minus value of, let's say, 3 to 5%. Because remember, in statistical analysis and business analytics, you're never going to be 100% finite in predictive analytics. This will at least give you a correlation to find something close to that linear line. This is an example of that. You see some outliers where they're not right on the line, but there are some that are close to it. So it depends how far away you are from that linear regression model. Now this is downward slope. It's a negative value, meaning that there's no correlation, but you can at least see the impact on the line linear regression and where each of the different groups, if you will, correlations and the red dots equate to that. It is important to interpret the estimated regression of coefficients. Coefficients are an ability to find the predictive value in the overall predictive variable. So predictive value of y, when each predictive variable exists, assumes a value of 0. It's not always meaningful. You must have an ability to identify when you have a correlation or not. Change in the predictive value of the response given in a unit increases to xj, holding all predictive variables constant. This could mean that, in an example, that each of your values have some equitable correlation with each other, that each predictive variable could actually have a similar or close to impact to the target variable, where all have a potential opportunity to be the same or not. So in conclusion, remember, in the linear regression models, predictions are subject to sampling variability. The prediction will change if you use a different sample to estimate the regression model. We must always remember that even though we're correlating one data set, if you bring in another data set, for this example of customer purchase behavior, and you're taking in a sample size of one set of customers to look at their age as their target variable, and how either income, occupation, or academic background is a predictive variable of that, Well, if you take another sample size, there might be a margin of error because you're looking again at descriptive data at a point in time. So use a estimate of intervals to plus or minus the margin of error. Remember, you always see in outputs of reports plus or minus, let's say 5%. That's almost a disclaimer because, again, it's not 100%. You're going to get to a 95% confidence level. So using a confidence interval as the interval estimate for the expected value. Normally, you want to see 95% or higher confidence level. At times, we call it a p-value of 0.05 or less. That's just the opposite, saying we have that 5% or less is not significant. It's not statistical. You are seeing 95% or more statistical impact or outcome. The prediction interval is always wider than the corresponding confidence interval. So again, predictability can have variations in it. Doesn't mean it's 100% of the time, but at least gets us to a place of more preciseness to say the more than likely outcome is this. I encourage you to take a look at the examples in the textbook for more on a walkthrough on some cases on how this works. And I thank you for your time here in Chapter 7. We'll see you soon. Thank you.